Now we've introduced two models, and what we said that perhaps we can combine the strengths of these models to build new models that are going to help us in modeling nonlinear elasticity with better, at higher quality, let's say. So we can, let's say, combine these models. In order to fit data better. Okay. Now, well, how would you do that? Well, I want to propose a strain energy function that is neither of the Fung or Neo-Hook model. We just called Fung the first model, remember, and Neo-Hook the second model. So I'm going to refer to them individually with its index of 1 or 2. Okay. And so I want to combine them in a very simple manner. Actually, I'm going to mix them through a parameter beta. And I'm going to take a certain factor 1 minus beta 1 of the first Fung approach plus the remaining factor C2. So here my combination is serving to ultimately fit data better. That's my goal. And I'm doing that through a parameter which is here called beta. And if I set beta equals 0, this term will die away and I will have the Fung approach. And if that parameter goes to 1, the value of the energy function that I am proposing will approach the Neo-Hook behavior. Okay? And if the value of beta is anywhere in between, then I will be able to model a behavior anywhere in between. In particular, my behavior does not need to have a slope that constantly increases or constantly decreases anymore. Well, what I can have is a slope that might look like that, or the stress-strain behavior, stress-stretch behavior might look like this, initially with a decreasing slope and ultimately with an increasing slope. So, well, then that's the way I'm going to do it. And once I pick a certain value of beta, then I can calculate the value of the stress, which is the derivative of always. This is true. And that's going to be equal to, again, 1 minus beta. Now, let me call the derivative of psi with respect to psi1 with respect to lambda, sigma 1. Sigma 1 is the stress versus stretch relation for the Fung model, plus beta, and that one is going to give the stress versus stretch relation that comes from the Neo-Hook model. I know what those functions are. I have already calculated them. And therefore, if I plug them explicitly in here, I will have a factor 1 minus beta multiplying the stress of the Fung model, which was E over alpha, e to the alpha lambda minus 1, plus beta E over 2 lambda minus 1 minus lambda. Okay? And now when I look at that model, I see that, okay, maybe some part of it is not going to do very well under compression, but this part certainly does very well under compression. But this part did not have any free parameter, but now this part has a free parameter, and moreover, I have yet another free parameter, beta. So I'm sort of combining the strengths of the two models, and I end up having reasonable stretch and compression behavior, tension and compression behavior perhaps, and moreover, I have now two free parameters. In addition to the Young's modulus for data fit, which is always good. It provides some flexibility when I'm trying to reproduce experimentally stated observations. Now, this ultimately, okay, good. So you can, if you go ahead and plot the way this stress versus stretch behavior looks, it's going to qualitatively look like this, but the exact view is going to depend what the value of E is and beta and alpha is. And also the range of all lambdas that you choose to plot it for. But ultimately, remember, always go back and remember what we're trying to do. You give me a value of stretch, and I'm trying to calculate, let's say, the value of the corresponding stress. Now, that's easy. that is one practical engineering concern. That's the given deformation, and you want to find the stress, and that is easy. Now, on the other hand, the converse scenario where you give me the amount of load or stress and I'm trying to find the deformation that this soft elastic material, non-linearly deforming elastic material is sustaining, to find that deformation, that's not so easy. And the reason it's not so easy, because if the left-hand side of this equation is prescribed and I'm trying to solve for lambda, well, there are nonlinear terms, 1 over lambda and exponential lambda that appears in the equation. It's a nonlinear equation, okay? So nonlinear elasticity is always accompanied by, naturally, nonlinear equations. And solving nonlinear equations is a challenge always. Now, but let me demonstrate a very simple tool that I'm going to talk about it now. And it's very simple yet robust, and we'll immediately use it in an example where we have to find out or answer such a question. Now, let's pick some representative values. I'm going to pick the stress to be 1.5 MPa. So suppose that's the stress that we're imposing, and I'm just going to concentrate on the neo-hook portion of this curve. So I'm assuming that we're only dealing with a neo-hook material, so I'm assuming here that beta is equal to 1, just as a simple scenario that we want to look at. And let us say that moreover, therefore, that's the stress, 1 minus lambda. I'm trying to find the lambda that delivers the stress for a Young's modulus, a special case. Let's take it to be 1 MPa. And I'm working in terms of MPa. And therefore, 1 over 2, this must be equal to 1.5. Or in other words, I'm trying to find the root of a function f of lambda. So if I multiply both sides by 2 and put this 1/2, which now becomes 3, to the right hand side, I'm trying to solve for something that is equal to 0, and that something is lambda minus 1 minus lambda minus 3 equals 0. I'm trying to find the value of lambda which satisfies this equality. Now obviously, so find root lambda. Now, obviously, first of all, if I can multiply everything through lambda, this is actually a quadratic equation. I can easily solve for it. But I want to retain it in this form so that eventually you could employ the method I'm about to summarize. If you already don't know it, you could employ it with other forms of stresses, such as those where you have exponentials. Now, what I'm going to summarize is a method that is called bisection. We have encountered nonlinear equations several times before earlier in the course. There I said that you can just use any numerical tool, but here I want to solve a numerical, explicit example. That's why we are talking about this method presently. So the bisection method solves nonlinear equations in the following simple manner. So first of all, we realize that we have a certain range within which seek the value of lambda. Okay? And that range is going to be in the tensile range, because I know that the stress is positive and hence it's tensile. In other words, lambda must be associated with tension, which means it's larger than 1. So lambda value is going to start from 1. Now, so when I plug in lambda equals 1 here, I see that I get minus 3. It's not equal to 0, it's minus 3. So F is equal to minus 3, which is less than 0. So obviously, as I expect, therefore, I will increase the value of lambda and f will become less and less negative. Eventually, it will be 0. But let's plug in, because I don't know the exact value of lambda and I want to estimate where it lies, the range, let's plug in lambda equals 5. If I plug in lambda equals 5, you'll see that 5 minus 3, it is 2, minus 1 over 5.2, 1.8. The value of f will be 1.8 greater than 0. So if it's 1, it is negative. If it's 5, it's positive. So the point where it crosses 0 must be somewhere in between. So now I know that the value of lambda lies somewhere in that range. So this is where the bisection method kicks in. It bisects this range and takes 5 plus 1 divided by 2, which is 3, as the next possible candidate. And then it looks at the value of f at that new value of lambda. If I plug in 3 here, 3 minus 3 is 0, 1 over minus 1 over 3 is the new value of f. And the value of f is negative, here it's positive, and therefore I'm seeking the root 0, and therefore the new range is that range. So I'm going to go ahead and divide once again by 2. Okay, so this was my first range of bisection. The second range is now going to be 3 to 5, and my next guess is the middle of that range, which is 4. If you plug in 4 minus 3, it's 1 minus that value, it's going to be 3 over 4, and it is positive. Negative, positive, my next range is going to be over here. So my next candidate is the middle of that range, which is 3.5. If you plug in 3.5 in there, you'll see that the value of f is approximately equal to 1 over 5. And therefore now this is positive, that's negative. This is my next range, and I would go ahead and take the middle of that range, etc. And I would carry on until the value of f is sufficiently close to 0. This is, as you see, it's a numerical method of somehow going towards the root of this equation. But the way I described, I will always make an error unless I'm lucky and I hit the value of lambda at which this is equal to exactly 0. Otherwise, it will always be very close but not exactly equal to 0. At some point, I will say that I have sufficient accuracy and I will stop. So that's the idea of the bisection method that I will use in the next example.